Alright, let's cut to the chase. How did I even get here? Well, the short answer is math, biology, and Alan. The long answer starts at the Olympics. What you're seeing right now is a compilation of arguably the greatest swimmer of all time, Michael Phelps. To put it simply, he is an athlete of Olympic proportions. I know, great pun. Anyway, Michael Phelps isn't just a world-class athlete because God decided to make him a fish. Alongside his phenomenal technique, he is a world-class physique which has been trained by years of discipline and hard work, just like any other world-class athlete. And this is me doing cardio to get gains. And if I'm being honest with myself, not doing it particularly well. Now, I know what you guys are thinking. Shobit, is this what you've been doing for the past month? And well, to be frank, yes. And there's 3 big reasons why. The first reason is simple. I wanted to get fit. A lot of my friends were working out, and I thought if this guy can lift weights, so can I. The second big reason was that a friend planted this idea in my head that Jack geniuses are really intimidating. And to be fair, he's spitting facts. Now, as for how that applies to me, the genius part is definitely questionable, although I do try. I fail a lot, but I try. But I do think a lot of exercise will help me look more intimidating, which I think is kind of funny, so we're gonna do it. Well, okay, Shobit, I hear you asking. That's only 2 reasons. What's your final one? Well, to put it simply, Alan. Basically, I'm friends with a guy named Alan. Actually, I'm friends with 2 guys named Alan. I'm talking about this one. Now, Alan is normally a pretty chill guy. July 8th, 2024, he decided, was not a normal day. These are Alan's estimated 1-rep maxes for every member of a particular group chat, including me. Now, some of these are pretty obvious jokes, but some of these aren't. And let's just say, I personally had some mild disagreements with it. Anyway, after that war kind of a message was sent, my motivations immediately became justified and valid, and I went to the gym the exact same day, which is how I ended up here. And this, dear viewer, was the start of Operation JACKED, a comprehensive scientific plan to enhance my muscle growth with steroids. Nah, I'm kidding, don't worry, I use calculus. But how do we even begin to connect those things? We have to start with a little known law called the force-velocity relationship. The force-velocity relationship is pretty simple. From a scientific perspective, it basically states that the amount of force that a muscle can exert is inversely proportional to the speed at which a muscle can contract. So that sounds way more complicated than it actually is, so I think it's best if I just show you some examples. If you think about it, when you run, it doesn't actually take that much force for your muscles to move each individual step. I mean, it's no exaggeration to say literal toddlers can do it. The lack of force exerted by our muscles is what allows them to move incredibly quickly, hence why running is possible for us humans. Now, if we look at the other end of the spectrum, lifting heavy weights requires your muscles to exert a lot of force, which is why you can't do it as quickly. Think about how long it takes to move heavy furniture into a new apartment, if you can even get a new apartment, or someone to move with. The exact opposite of the running scenario. In exchange for force, you've given up speed. Basically, the more force a workout puts on your muscle, the less quickly you can do that workout. This inverse relationship can be pretty easily represented on this graph, where the y-axis is force and the x-axis is velocity. What's also really cool about this is that almost every single workout can be mathematically represented somewhere on this graph, from high-intensity cardio to strength training. Now, if you're a little bit more familiar with math and science, you'll know that the direct inverse relationship I just described can be represented by this equation. Other famous inverse relationships that can be represented by equations of similar formats include Boyle's law and Ohm's law, both of which you may have learned in school. But what's most relevant and interesting about this equation is that it's actually not new. You may have recognized it earlier, especially if you've taken a physics class, but this is actually the formula for mechanical power. That's right, this whole inverse relationship, from the equations to the graphs to even the examples, they're all just a fancy way for scientists to say that muscles move in a constant power. More muscles means you can exert more power, and less muscles means you can exert less power. Which is the most obvious thing ever. They really could have just said that instead of all of this. Regardless, this gives us an interesting way to maximize our muscle growth. As stated earlier, the amount of muscle that we have is directly correlated with the amount of power that we can exert. So as a result, in order to change the amount of muscle that we have, all we have to do is change the amount of power that we can exert. Optimizing our change in power will allow us to optimize our muscle growth. So naturally, our next step is to figure out what our change in power, or dP over dt, actually is. And this can be done pretty trivially, using the power formula that we discussed earlier and the product rule from calculus. This gives us the following equation for our change in power, or in other words, our muscle growth. The F terms represent force-intensive exercises, like weightlifting or resistance training. The V terms represent velocity-intensive exercises, like cardio. But wait, I thought cardio kills gains. Well, not according to this equation, apparently. And to understand why, we have to ask ourselves a pretty important question. How does doing this somehow lead to this? The answer is hypertrophy. Hypertrophy is the process by which your body takes smaller and generally weaker cells and then enlarges them. This generally has the effect of taking the organs that the cells are part of and making it bigger and stronger. Hypertrophy does a lot of things in the human body, but perhaps most importantly for us, it is almost solely responsible for muscle growth. But how exactly does it do that? Well, to put it simply, exercise breaks muscle. No, I'm serious. Let's pretend that this bundle of toothpicks is a muscle and each individual toothpick is a muscle fiber. When I exercise a muscle by applying force to it, it's the same as when I apply force to this bundle of toothpicks. Just imagine this toothpick muscle doing a bicep curl. Anyway, as I'm doing that, you'll notice that the individual toothpicks are breaking apart slowly, eventually causing the whole structure to start to break down. The same thing starts to happen to muscles in real life when you start exercising and working them. When your muscle fibers break like this, it releases chemical signals to the rest of the body. Those chemical signals in particular basically tell the rest of the body that that muscle in particular is under a lot of force and tension. Your body, being significantly more effective than every single world government, decides that the obvious problem of your muscles turning into Italian war crimes is in fact a problem. As a result, your body not only provides the materials to rebuild the muscle, but to rebuild it in a way that's bigger and stronger. Now, at this point in the video, I think it's pretty easy to understand why force-intensive workouts are so important to muscle growth. Putting a lot of force on a muscle causes it to break, and when a muscle breaks, it basically undergoes that whole process we just discussed 15 seconds ago. But why is velocity so important? After all, if I take this muscle fiber and move it really fast instead of really forcefully, it doesn't do anything to break it. Well, remember those materials I got to build the new muscle earlier? Well, they didn't just poof out of nowhere. I had to take a long and arduous journey from my room to the kitchen to get the toothpicks from one of the shelves, alongside 4 coconut cookies because diabetes is a liberal hoax. It stands to reason that if I ran towards my toothpicks instead of walking towards them, I would have been able to get my materials a lot more quickly and as a result finish building my muscle model a lot faster. Now, your body doesn't have a little showman walking around collecting material to build muscle. But what it does have is a highly efficient circulatory system. A circulatory system that gets progressively more efficient the more and more you do high-velocity, low-force exercises. That's right, cardio doesn't kill gains. In fact, especially when paired with strength training, cardio actually helps you get gains faster. And it does this by increasing blood circulation, therefore allowing for faster transport of materials necessary for muscle growth. And just to quickly discredit the logic behind this common myth, while it is true that your body can burn muscle mass, it only does so under the most extreme of circumstances. Your body first burns carbohydrates, or all the sugars and starches that you ate in the last 4 to 8 hours depending on your genetics. After it's burned through all the carbs, your body then starts to burn fat, which is a huge energy source that builds up over the course of years. This is actually the main reason why a keto diet works. And if you want to learn why, you can pause here to read my rant. Anyway, once you've burned through all the carbs you've gained over the course of a day, as well as through all the fat you've gained over the course of a lifetime, only then does your body start actually burning protein and muscle mass. At that point, you're doing an inhuman amount of exercise and cardio. Basically, in 99% of scenarios, cardio does more good for muscular growth than bad. Now we have a sufficient biological explanation as to why this formula works, which gives us an even better reason to start maximizing it. And just like last video, in order to do that, all we have to do is find the derivative and set it equal to 0. When we do the proper and necessary steps, we'll get this as our next derivative. Which leads us to our final problem. Actually solving this thing. Now, if you think that the differential equation that we ended up with is actually hard to solve, then you'd be surprisingly incorrect. Because it's impossible to solve. This is a second-order non-linear differential equation with 2 independent functions acting as separate inputs. Basically, Wolfram Alpha couldn't even dream of calculating this, much less me. In order to have any hope of solving this equation, we have to simplify it. And in order to do that, we have to modify the equation with something that math can never take into account. The real world. Basically, in the gym, you have the option of choice. You don't just have to do velocity-intensive workouts and force-intensive workouts. You can quite easily do both. And remember, because they're inversely proportional, velocity doesn't really affect force-intensive workouts, and force doesn't really affect velocity-intensive workouts. workouts. Furthermore, when you're running reps or doing miles, your velocity and force respectively remain constant for both, as exemplified by the graph over here. Basically, for real-world exercises, if you're doing force-intensive workouts or velocity-intensive workouts, the other variable is basically constant and negligible. In other words, we can essentially ignore it. As a result, I decided to split the original equation into two separate weak equations. One focusing on force-intensive workouts, and one focusing on velocity-intensive workouts. By losing the relatively unnecessary information of one of the variables, we've created two solvable differential equations that maintain the general form of the original. So let's actually take a minute to solve the equation. A little disclaimer before I start though, I'm using the force equation for this example, but this entire process applies to the velocity equation too, because they're literally the same equation, just the variables are switched. Any kind of differential equation like this, where we can't just straight up algebra or integrate our way out of it, we generally start by guessing a solution. In this case, our guess is that the solution takes the form of e to the rt, where r is a constant. The main reason we chose this function in particular is because if you've taken Calculus 1, you'll know that this equation has really nice and easy general derivatives to work with. Anyway, when we plug our guesses into the original equation, we'll get this as our new equation. Now, in order to get to a general solution, all we have to do is solve for r, the constant, which, after we divide everything by e to the minus rt, is just a matter of solving a quadratic equation. R is equal to -1, and once we plug that in alongside an arbitrary constant, c, we'll get our final general solution. Which means we're done, right? If we go back and focus our attention on this part of the equation, you'll notice that it's squared. Now, if you were just doing this algebraically, this wouldn't mean much, but since we're solving a differential equation, it means that it can be written like this. And the two possible roots, although identical, imply that the equation has two separate independent solutions. So while this is a solution to the differential equation, it is not the solution. We have to find another one, which means we have to go back to guessing. Now obviously, our second solution can't be in the form of e to the rt. We already have a solution like that. Instead, we're going to make a guess with the second easiest form to work with, or t times e to the rt. However, since we know r is -1, we can just replace it with t times e to the -t, and work our way through the derivatives from there. After plugging all these into the original differential equation and testing it in a similar way to how we tested e to the rt, we can confirm that this is in fact a general solution to this differential equation. Now, to get the general solution, all we really have to do is add these two terms up, and we'll finally get the equation of maximum gains, which, when plotted on a graph with the correct constant conditions, will give us this curve. It tells you how much you have to work out over time to maximize your muscle growth. The horizontal asymptote here is solely controlled by the d term, and it basically represents how much you want to be able to lift, or how fast you want to be able to run. The initial value term, or how much I actually can lift at this moment, is controlled by the equation d plus c1, or c2. I adjusted the constants to my specific preferences and, well, started training. And train I did. I diligently followed the curve as best I could for roughly 3 to 4 days a week, succeeding and failing along the way. Generally a lot more failing, if we're being honest. But despite it all, my ambition, nay, my desire to beat the allegations of that lame man Alan persisted. Luckily, my persistence was rewarded. I have muscles now. I can actually see these things and like touch them. It's weird. Anyway, for reasons I really don't think I have to explain, I won't be showing any more of my muscles on the internet. Overall, I'm pretty happy with how my body looks now, and I think that means that this video was a success. Is what I would like to say, but there's still one more thing that I have to do.
Alright, Alan, here look. 140 pounds. That's 130. Hold on. 140 pounds. Alright. Your max is supposedly 135. I wish I had barbells. But they don't. They're not in this gym, so we're gonna have to do it with machines. Sorry about that.
Well, if that doesn't deserve a like, subscribe, or a comment, I don't know what else does. Seriously, it's free, it takes less than 10 seconds, and it helps me out a lot. So if you really enjoyed this video, which I assume you did, considering you made it all the way here, please consider doing so. With that being said, thanks for watching, and see you soon. Trust me, it'll be worth the wait.